The average German family spends something like 10 to 20 hours a week playing board games.
Test 1 2. Okay, for our online audience, we're going to start in just a few minutes. We're still getting set up here in the room. All right, we'll go ahead and get started. Grab their lunch. I'm Dean Bickerton with the president of ISA New Orleans section. Just going to give you a quick update on a few things going on with the section before we turn it over to our presenter today. First off, we are in the middle of our sponsorship drive. So these are our current sponsors from last year, and some are in the process of renewing their sponsorship. But I just want to mention to everyone, if you work for a company and you're interested in sponsoring the section, it's $150 a year. We put your logo up on our website under our sponsors page. We also present our sponsors page at every meeting, and then we give our sponsors the opportunity, kind of the first opportunity, to present content at some of the meetings. So Dennison Consulting is sponsoring this meeting, and then is providing the content for the meeting as well. So appreciate that. So the sponsorship helps us keep the meeting costs low. So it allows us to have the lunches free for our members and only $10 for non-members. So it's very, very reasonable cost. It also gives us the funding to do some of the things that we do in the community, some of the outreach. So we are involved with FIRST Robotics. We're going to be involved in the STEM Fest event that's going on at the Superdome in October. We get involved with the new Children's Museum that's being built in City Park. There's a fundraiser that we do for that every year called the Family Fun Eat and Run. So the sponsorship dollars help us to do some of those outreach events, help keep this section running, and keep costs down for our members to attend the meeting. So if interested in sponsoring, please do. And then I want to talk about the next meeting. So next month, October, the section is going to actually sponsor the IEEE meeting. So typically, IEEE IAS, which is the Industry Application Society, meets here at MS Bembo, typically the first Wednesday of the month, and those topics are power-related topics, typically, IEEE topics. We're going to be the sponsor for the next meeting, and what we're doing is we're bringing back a speaker we had last year. We had a fellow by the name of John Lawrence Bush, who we brought in last year to do a session for us at UNO. We were doing a meeting at UNO to kind of help build the UNO student section and get more involvement from students. So we brought a guy in who wrote a very interesting book on the history of the first steamship to cross the Atlantic, a vessel called the Savannah. And a very interesting topic. He put a very good engineering spin on the topic, talked a little bit about the culture going on at the time, talked about the things that they had to overcome to get the ship built, kind of the perception that they had to fight against with people saying, why are you going to do it this way? We've been sailing with wind forever and ever. So he's going to come back and he's going to do a follow-up presentation to talk about the technology shifts and how it's hard to convince people sometimes to think outside the box and do something new. And so he's going to talk about how long it took for people to realize that they could use artificial power as opposed to natural power. And he's also going to talk about how there's a kind of a resurgence even of hybrid systems where natural power can supplement artificial power. So there's a picture here of this vessel that's an artificial powered vessel that actually has a sail on it that is using to supplement the power. So we're going to talk a little bit about hybrid systems and kind of how hybrid systems are very popular today. So real good speaker. He's actually going to be in the area speaking for the aeronautics community that evening up on the North Shore. So while he was coming back into town, we grabbed him and we're going to have him talk down here at the IEEE meeting. So next month, it won't be on a Tuesday, it'll be on a Wednesday, and we will be supporting the IEEE meeting. Of course, ISA members and non-members are welcome to attend the meeting, and this will be posted on our website. You can sign up for it just like any of our other meetings. Okay. And with that, I'm going to turn it over to Diane Dennison, and then she also has help from Matt Moore, yes, who's remote. And so I'm going to talk to you today about power quality and energy management. Some of you all may have met Diane a couple years ago. You did a presentation on I think analytics, and this was quite some time ago. Maybe 3 years ago. Now.
Maybe, I can't remember.
But anyway, so Diane's back. She's also been a sponsor of the section, so we appreciate that. And she's going to talk to you about why power quality matters.
Perfect. Thank you, Dean. Hi, I'm Diane, and on the phone remotely is Matt Moore. He's one of our engineers. He's a PE, and he's up in Pennsylvania today on site. So he'll be answering all your hard questions. Any easy question, I will be glad to try to take.
Thanks,
so
Diane, I appreciate that.
You're welcome. Matt, just have your phone on, please. So just to get started, we wanted to talk about power quality and why it matters. And prior to getting started today, I think was talking earlier about this concept of sustainability, and we all know innately that we need to use power and energy more efficiently. I think it's an understood statement. So today we want to talk about, am I driving this here? Okay. Today we want to talk about just really why power quality matters, just briefly, some of the business drivers in the focus. And we'll get into just the basic refreshers on power quality, and Matt will pick up from there. And then from our standpoint, really taking power quality as a total quality management approach, from assessment to delivering of appropriate monitoring systems, to the analytics, to the insights. So we're going to walk through what we believe are the necessary steps to really address thoroughly power quality related issues. Talk about some of the challenges to deliver these solutions as an industry, and then we'll share a software demo of an ISA 101 compliant HMI screen and the dashboards, including the historian and some of the reporting pieces, and then the next steps from there, and discussion too. So briefly, why does power quality matter? Well, we know it's the largest unmanaged industrial expense. In fact, manufacturing utilizes about 30% of the nation's energy. And so we want to focus on helping them reduce cost in areas that are of greatest importance to them. We know the 2015 UN Climate Change Initiative, we talk a lot about sustainability and better using our resources like water and CO2 emission reductions, and also utilizing energy more efficiently. So about 60% of Fortune 100 companies have a written statement, a written policy. It's all over their annual reports, talking about they want to reach certain targets, typically mapped to target dates like 2020, 2035, and 2050. And you'll read that depending on the company, saying we want to reduce energy cost and consumption 20% by the year 2020. Well, that's a lofty goal, and it's a good one to have, but how are we going to reach that objective? And what processes are we going to use, and how are we going to measure really effectively mapping into that objective? So many of these companies are implementing programs. Many of these targets are not being met depending on the company and the target. If we dive down deeper into power quality related issues, I'm going to take a little data point from Rockwell that I've read repeatedly. Rockwell believes, and I believe it to be the case as well, 30 to 70% of unplanned interruption downtime is caused by poor power quality. We'll get into some of the details about that later. So we know that power is necessary in the production cycle, and we know that it's a high cost driver. And we also know that when things go bad, the consequences are great. So that's why we've chosen to focus on that. So if we focus on the business drivers of our customers and operators, we know they want to just thumbnail. They want to reduce cost, decrease disruption. They want to improve maintenance, improve the efficiency, their overall equipment efficiency, improve quality, meet the regulations, and maybe do some more things down the road in terms of efficiencies, moving from basic analytics to maybe advanced analytics and preventive and predictive diagnostics. So again, just a summary piece. We know it's important. We know in the top right quadrant, 30 to 70% of the disruptions are caused by poor power quality. And why is that the case? Well, we have an explosion of electronics on the plant floor in our world, 50 billion smart devices by X date. You know, we hear about it all the time, and our plant floors are getting more and more complex and more filled with electronics. We also know it's a two-way power street on the plant floor. And we know that some of these new technologies with positive intended consequences to slow down your motor drives, to decrease your energy cost and consumption, create nonlinear loads at the same time, right? So you've got variable frequency drives, you've got LED lighting, you've got different sources of potential causes of poor power quality. And in the top left-hand quadrant, you see, well, but if all these things are true and the consequences of poor power quality are so significant, why is it that only 15% of companies have a program in place where they're actively utilizing software to, in real time, measure and monitor power quality attributes? Well, there's a combination of reasons why these end-to-end solutions have not necessarily been driven out. First of all, it's a very complex problem to solve, involving platforms, people, performance, focus, and money to deliver solutions. We know that connecting into often what are smokestacks of data sitting behind the DMZ plant wall is daunting and difficult, because these machines speak different protocols, and connecting into those machines is difficult at times. And the data resident within the machine is coming to us in different structures, different formats. So it's a complex, challenging problem to connect to the data, collect the data, and assemble the data. And certainly crossing the DMZ creates security issues. And crossing the DMZ means your OT and your IT teams need to usually cooperate, and that's not always a gracious place for your IT teams and your operations teams. And so we know to get to our required outcome, we need to solve the problem collectively by working with the OEMs and the integrators and the customers. Because in the bottom left-hand quadrant, we know that when power is not of highest quality, we have disruptions In some vertical industries, the total downtime cost per hour is very, very high. So for example, the average per hour downtime cost in automotive might range from $200,000 to $5 million per hour of downtime. And depending on where that disruption takes place in your process, you can also have tremendous degrees of scrap and rework. I've also thrown in, for good measure, regulatory issues. If you're in the pharmaceutical business, for example, and you've got downtime in that sector, you might have a disruption in your compounding process. Tire and rubber would be a great example also, where those materials are not of high enough quality to be sold, so they need to be scrapped and discarded, which creates an EPA or an FDA reporting issue. So, and not to least of which, when you're not running efficiently, you can create potential integrity and reputational damage with your customers. So I'm gonna let Matt pick up for a moment and talk about just kind of the basics of power quality. And Matt, I'm gonna be driving the presentation. So as you continue talking through this on the standards, I'll continue flipping through your slides.
Okay, thank you, Diane. First of all, I apologize for not being there, and hopefully you can all hear me okay. So, yeah, the basics of power quality. I'm assuming by the audience who's in attendance that everybody understands about power quality and it being an issue, regardless of what your facility is. We have IEEE 1159, which governs power into the facility. Then we have IEEE 1134, which is power within your facility. Now, the problem with those two things is that they don't exactly correlate some of the time. So what we like to do is we like to monitor the incoming power in the facility so that we know what is actually coming in. Now, the problem is that even if you have good power within your facility and you have several outages, sags, swells, so on and so forth, it may not always be your fault. And the only way to know that is by looking at power that's coming into your facility. Once it's in there, there's really nothing that we can do with it. Once it's in your facility, there are things that we can help with, such as if you have drives, and you have LED lighting, some of you probably still have fluorescent lighting. All of those factors have an impact on the power quality within your facility. One big item that we also encounter in plants that we go into is grounding problems. And those, unfortunately, are some of the hardest problems to detect. If we have a good power quality monitoring system, it will be easier to be able to detect those problems. So we like to go in and look at the facility, but then also you have to be able to visualize and act on what's going on inside of it. So Diane likes to do these charts, as you can see on the screen there, and she always likes to highlight one of them in a different color. So the green, as she puts it in the slides, is ISA 101, which is the standard for visualizing an HMI. So all of the things leading up to that are items that we do or items that you can do inside of your facility. But then the final one is, and why it stands out, is because that is where it is up to the plant operators and the plant technicians in order to enact what is being shown to them by the power within their facility. Diane, can you go to the next slide, please? So in the next slide, samples of power quality and the event types. Everyone knows that you have voltage sags, swells, harmonics, transients, but what are these all caused from? And that is the most difficult part of any engineer's job, is to figure out why are these things happening. People on the plant floor, most of the time, they're just fixing problems, and they're a machine goes down, it's their job to get the machine up and running. Well, our goal is to make sure that that machine hopefully does not go down, but if it does go down, we can figure out exactly why it went down, which goes back to the power coming into the facility. If we can determine, hey, you have a neighbor who's up the line from you who seems to be starting large motors at various points in time, and it's causing a disruption to your facility, which causes relays to drop out, which causes, for some reason, some motors to go below their threshold, some starters to go below their threshold. Why is that equipment shutting down and then having to restart? It may affect, for some of you, if you have processes where heating is a critical component of your process. At one point in time, I was in a plastic cup manufacturer, and they had an incredible amount of resistive heating, and they were getting up the line from them. There was a factory who was turning machines on and off, and it was creating havoc on their resistive heating because of the electric drops and the sags that it was causing on their facility. Next slide, please. So if you look at this slide, it's actually a very interesting slide, and I really do like this one because it actually gives you a very very good frequency of occurrence of different types of voltage phenomenons and power phenomenons coming in your facility. So, and it's pretty self-explanatory, and the cost versus the frequency of what happens. If you have, typical sags, anyone can have those very high frequency of time and for the most part, very low dollar amounts as far as machines shutting down, starting back up, maybe nothing's happening at all. You may not even know it. But as you move down in the scale to very low frequency of occurrence and then move over on the scale, you can see that transient phenomenons, even though they're a low frequency of occurrence, are very high dollar amounts to fix. And all of the occurrences in this chart are items that we like to go in and we like to try to figure out and try to predict what's happening so that we can be proactive for your plant, so that we don't try to react to what's happening, but that we can try to fix what is actually coming in and what's going on inside of the plant, regardless of where it's at. Go ahead, Diane. So what are power quality basics? Everyone knows that, especially with the hurricane that just came through, Hurricane Florence, weather certainly creates havoc on the power grid and the power infrastructure, no matter where you're at. Guys driving down the road, hits pole, power goes out. Somebody is doing construction, their crane falls over on power line, happens all the time everywhere. Trees, squirrels happen to be climbing across a wire, jump between two of them. Maybe they're jumping across the terminal of the transformer. The squirrel is no more, and you lose power. And I'm going to let Diane explain the Gladys Kravitz because I'm
trying to make this day a little bit more entertaining. And for some of you, you know who Gladys is, and for some you don't. But she's the aggravating next door neighbor in Bewitched, who just aggravated Darren and Tabitha and Samantha to no end. And so you can have an aggravating next door neighbor, to your manufacturing facility that's wreaking havoc on your power. And I call that Gladys Kravitz, right? That through no fault of your own, you're living a good life, but Gladys is creating power events, to Matt's story before, turning on and off of motors randomly next door. Go ahead, Matt. I'm sorry.
No, you're fine. So Gladys Kravitz, listen, I don't have any personal knowledge of Gladys Kravitz, okay? That's more Diane's MO. So that's why I let her talk on that point. So on the starting of large loads, motors, port connections, and grounding, I like to give an example of or actually a water plant that I was in, because they had two different pump stations that were in the plant, and they pumped two different sides of the water, two different distribution points in their water system. And there were two high service pump stations. One had 4, I believe, 250 horsepower pumps, and the other side had two 600 horsepower 15 kV pumps, and the other ones were 600 volt pumps. Every time those 13 kV pumps turned on, they would drop the voltage down inside of the plant enough where they had all of their relays would drop out. So they would obviously drop below at least that 10% threshold. When those relays would drop out, the other pump station would actually go offline because the valves would start to close, which would automatically start to shut down the pumps. That would happen probably 3 or 4 times in an operation cycle, which their operation cycles were about every 12 hours. So by starting of large loads, large motors, everyone can see, it was very evident to see what was going on inside of that plant. Now, correlate that to what you guys see in your factories and in your plants that you have. It's no different, because you have machines that maybe are running all of the time, maybe are running at a set speed all of the time, maybe they're starting and stopping. So even within your own facility, to be able to understand what's going on, to be able to sequentially maybe start motors, to either ramp them up or ramp them down, can have a great effect on just the electrical infrastructure of your facility alone, no matter how big it is. And this was a big water plant. So it can have a great effect on what's happening. Port connections, everyone knows you got to torque them to what the manufacturer says. Grounding, like I said, grounding is one of those issues that is incredibly difficult to isolate and to fix until, but the thing is once you fix it, it's amazing because everything goes away. That is the nice thing about grounding. However, like I said, it is just incredibly difficult to fix. Immediate long-term damage sensitive equipment, yes. Everything on the plant floor, I should say everything, but a lot of things on the plant floor, just as Diane said, is all electronic now, okay? You don't have the large starters hanging there on the side of equipment where the operator's standing there pushing buttons, starting and stopping, or manually ramping things up or ramping things down. Everything is done automatically. You know, you have to push out so much product. The only way to push out so much product is to make sure that your systems are tuned so that you can be able to ramp up and ramp down to be able to push out the amount of product that you need to do. And the explosion of deployed technology, you know, the VFDs, LEDs. I remember when I was at a trade show, I can't remember, it was probably 10 years ago, and they were selling, GE was selling LED light bulbs for $20 a light bulb, a 60-watt light bulb that was to replace a 60-watt light bulb in your house. And she goes, I remember asking her there how much it cost, and she told me $20. And then she said, but it'll last forever. And I said, I'm sorry, I don't mean to offend you, but I got 3 kids. There's nothing in my house that lasts forever. So to the point, LEDs now, in just 8 years of time, number one, have dramatically come down in cost because you have many manufacturers now making them. And the difference between LEDs and fluorescent bulbs is LEDs need a driver, just like a VFD is a driver. An LED needs a driver, and a fluorescent light bulb loses a transformer. So when you need a driver, you have now another sensitive electronic component that is susceptible to some type of electronic either discharge or charge on your electrical system. Whereas with a fluorescent light bulb, you know, you got a transformer up there essentially. You have a ballast, which is copper and iron. Yes, you can still have problems with that, but the fact of LEDs, yes, they're energy efficient. However, it now comes with its own problems as a result of being more efficient. Go ahead, Diane. So our approach to power quality. Go ahead, Diane. it's not real. We don't like to think it as rocket science, but we like to think of it as exactly trying to figure out exactly what is going on inside of your factory. The best people who know what's going on inside of the factory are the people there. So it is imperative to us that we sit down and understand with plant personnel, how is your plant running? What are you doing here? What are you trying to accomplish? What are your problems? How can we help you solve your problems? We'll walk through your plant with you. We'll sit down with you. We'll sit down with the plant personnel, as many people as we can, to understand what is going on inside of the plant and what the problems are. We'll review your key documents, your one-line diagrams, any information from the power company that you may have, anything that we can do to help our assessment of your factory is something that we see as valuable for us helping you, because our ultimate goal is to help you. We want to make sure that, number one, you're pushing product out your door, because the more product that you push out the door, the more money that you're making. We analyze and interpret your information, anything that you can get us, anything that's helpful. We engineer, design, we deliver those documents to you in any manner that you like to see fit. If you don't have those documents, if you don't have one-line diagrams, if you don't have control one lines of your equipment that shows all the instruments connected to it, we can build all of those things for you. So I don't want you to see that as a hindrance if you don't have those things. It's something that we can provide as a service to you. It's just something that we want to do so that you know what better is going on inside of your facility. It's important for us so that you know what is in your facility. Even after we walk away, after we help you, we want to make sure that you're happy with what you have and that you know what's there. Go ahead, Diane. This is just a basic screen that we have built for customers in the past. It shows a voltages, it shows current. By that, we can come up with total harmonic distortion. We can come up with the total kW, total kVA. By those, we can calculate your power factor. We can figure out all of those things, and we can build an HMI screen for you so that you know exactly what's going on inside of your plant. We can build it like this. We can build it per motor. We can build it per equipment. We can build it per line. But it gives you a snapshot of what's going on in your factory, in your plant, so that you can look at a computer screen. You don't have to walk around and look at every motor. You can sit in one place and you can see, oh, why do I have a high current here? Why is my voltage off here? You can start to see trends going on inside of your equipment. You can start to see, why am I getting a sag here but not a sag here? Why am I getting a swell here? Why am I not getting a swell here but it is here? So it's intuitive. It can build you graphs. It can build you trending charts so that you're able to see what's going on inside of your plant. Go ahead, Diane. So our customized reporting, we look at with the information that you have out there. Every factory is going to have some type of PLC. It's something like a Delta V system, which is a higher level operating system, or maybe it's just basic PLC control. Everybody has operator terminals, data loggers, and all of that information that is brought into those PLCs needs to go somewhere. If it just resides there, that's good, but it doesn't tell us everything that we need to know. We need to get that information out of the PLC so that we can analyze it in some type of historian or database, so we can then create a reporter for it in what we call Excel reporter, and we can then build it into an operations and management system for you. Every plant's different. Every plant has their own way of doing things. They have their own criteria that they want to see. Every operator is different. Every plant I've been in, every operator wants to see something different. It's not something that we can say, here is a canned product, this is what we're going to do on every time, because it doesn't work that way. Everybody likes to see things a little bit different, and that's okay. Everybody's different. But the basic information is the same. It's just a matter of sometimes how people want it displayed. So we can display it however you want it displayed. You can get a paper report if you want to do it that way. You can go to a web page and see what's going on. Some people like being able to be on the factory floor, having an iPad out there and being able to log into their network and see what's going on right there. Some of them don't want to do that. Some of them just want to have the computer residing in an office where they can go to their interface and view their screen and see what's going on, but then walk out and see what's going on. That's if there's a problem or if there's not a problem, or be able to tell people what's going on. So it's scalable, and it's up to the end user ultimately how they want it to, for what they want to accomplish.
Okay, thank you, Matt. Just on this, if we just think architecturally, forget about what Denison does for a second. This is the challenging part, is connecting into all of these disparate devices that often are smokestacks of data sitting behind the DMZ. And typically, I'd like to say the traditional architecture is application software sitting on a server in various smokestacks of data. What we've done, which the industry is moving to, and again, it's not as important about what we've done, it's where the industry is going and where it makes best sense to solve the problem. These pieces are collapsing in cloud-based architectures. So you've got cloud-based systems with connectors into 100+ devices, speaking standard industrial protocols. So you've now taken this capability that speaks to most of the machines at the languages they speak to Matt's step one that he talked about before. Again, regardless of Denison, it's part of a process that needs to be done. That last piece of this, engineer, design, and deliver, you need to engineer the customized monitoring systems to pull the relevant data that you need to really make insightful decisions, like the waveform capture. So if you know a pure power quality signal is a pure sinusoidal wave, you want to be capturing that waveform and all of the other attributes that Matt talked about before. So this piece of it is not only delivering insights from the assessment, but it's also designing and engineering customized monitoring systems that then are installed on the plant floor at various strategic parts, like the PCC room, the high voltage room, or the line side, to get that full reading from the plant once the power hits the plant, and then how is the power utilized throughout the plant. So as Matt indicated, your data is captured and collected and analyzed and interpreted. In that example I just shared, if we're connecting into a system, a monitor, a PLC, a switch, we can pull data every 137 milliseconds. Why does that matter? It matters because the chart he shared with you before about the duration of some of these SAGs, you want to capture that information that often goes unnoticed. So if you don't have the right monitoring systems and you don't have the right Petri dish, I call it here, you're not going to be capturing the relevant data in one place to make that insightful decision. And then as Matt indicated, you then take all of that insights that you've pulled in and report to whoever needs and wants the data to make an actionable insight, action from there. So some of the things that go into this, and we'll do a demo in a second, ISA 101 is the industry standard for the next generation human-machine interface. Lots of conversation about that. In summary, it's a standard philosophy, a life cycle approach, a guide, a format, the colors to use, the fonts to use, how the information is represented, that kind of thing that went into years and years of formulating the standard for that HMI interface. So Matt talked before about the standards that we are really looking at that are germane in this space. The 1159 power coming into the plant, 1134 how's power used throughout the plant, 18.2 was how are alarms being reported, thresholding of alarms, notification, that kind of thing. And then 101, which is why I made it green, is where the rubber hits the road. That's where your data comes to an interface where an operator can hopefully make heads or tails of it. What am I looking at? Why is this important and how do I act on it? And so your interface, your HMI, has to be able to communicate, to collect the relevant data and parse out data relative to the tsunami of data available to the operator, and looking at the velocity of the data. It should be coming in at a sequence. The veracity, is this valid data for me to interpret and take a look at? And then how is the data represented in a user-friendly format that's recognizable, using diagrams, using the gauges we'll talk about in a second. Is the operator feeling like this is something that's recognizable to me that I can act upon? So you have to think big in terms of this element, right? The HMI has to be considering of the cognitive brain. How is someone making a decision using the information presented? But then behind it is the engine supporting that. Is it SCADA ready, for example? Is it evolvable? Can I add a myriad of users? Can I add different data sets? Can I modify and customize the screens? Can I perhaps do, advanced alarming and hierarchy, historical trends, that kind of thing, and have a historian? So the bottom line is human factor engineering, cognitive brain, all of that goes into designing an HMI that's user-friendly, that's usable. Because all of the work we do up to that point, if we can't demonstrate the data in a format that's actionable by the user, it doesn't really matter much what we do. So this is usually where the rubber hits the road between your designers, your operations team, your programmers, your operators, really getting together and hammering out their process flow, their workflows, their diagrams. It's a collective effort here to make that HMI usable. And then we can, again, deliver a myriad of reports. This is an eye chart, but reports that would be germane would be maybe an OEE report. How efficient are your machines running? An alarming report. What is your historical alarms? What are the trending of alarms? What are the severity of the alarms? That kind of thing. And then eventually maybe health and diagnostics reports, right? So if we're pulling in power quality information and we can correlate that with maybe health diagnostic information on drives and key machines that are impacted severely, then we can then correlate that data and show that, oh, this is the impact to that drive. This is the impact to that machine, right? Not only looking at the OEE data, but we're now moving from being aware of something to predicting and preventing and improving maintenance from that. Well, I'll show our screen in a second. So you've got KPIs and dashboards and templates that are really designed to your KPIs to provide a myriad of reports that I went through before, and your user support and your user acceptance is critical. If the user does not use the HMI, it really doesn't matter much what we do. So that interaction has to be important, and the evolution path of that HMI has to evolve to the point of moving from an awareness to an action to a prevention and a prediction, right? You kind of overlaying machine learning, some additional data coming in. So if we could go just through a sample of our screen, not of our screen, but a sample. I always like to show how things are really done and used, because it is more insightful than hearing me talk. So Dean's pulling up a demo that we put together for just a prototype. So imagine that you're running a entity with 200 factories, and this is basically a Slippy map, geographic map, screen sample, where the plant manager can go in and see you've got the thumbnail tacks that are green. Green means good, red is bad, yellow is an alerting condition, for example. So at the beginning of the day, I'm the plant manager. I can go in and look at my 4 plants, the left-hand drop down in Boiling Springs, Monticello, Mount Holly, Zachary, and I can see they're all green. That's a good thing. I don't have anything hugely to worry about. But if I'm interested in looking at Zachary, for example, so Dean's clicking on Zachary. Now, this is one thing we realized with this particular exercise. To Matt's point earlier, sometimes when we work with clients, they don't have all the documents that we need, or the information is stored in a tenured person's head and not necessarily shared. So there's a disparate level of documentation. In this particular case, I said, why don't we make a dashboard with that power diagram so that the operator can see, by example, here's a power diagram on a specific line. It's showing the master controllers what's hanging off the line, so they can very readily see, oh, this is exactly what I'm looking at. And then if I want to further show, Dean, if you could go to the left toolbar down to quality. Now, we're not connected, but if we were connected, the top right-hand box under communication, those boxes would not be red, they would be green. And we would be remotely connecting securely over DNP3, which is a layer 2 transport protocol that the electrical utilities use. It's a secure protocol. So we would be connecting DNP3 into a power monitor, and we are pulling data every 137 milliseconds. So unlike where the screen is showing right now, if it were green and we were connected in, the data would be flashing at us and we would see different trending. And so as Matt talked about before, the closest box to the right of the communication are your statistics. We're pulling frequency, kilowatt kVA, power factor, some voltage current imbalances, and then the big green squares in the middle, total harmonic distortion. And Dean, if you could just click on one of those big green boxes, by example, you know, I'm the operator, I'm playing for the day, I want to see my historical data viewer. If I can, again, if this were connected to a live site, we would be seeing data coming in sequence, in time sequence, real time into the screen. You can pull down the drop-down menu. You see you've got a historical viewer. You see 1 day. We can pull data from 1 second to 5 years. So I'm looking at what is the trending data showing me? What are the events showing me? By all of these factors, I can then export my data to Excel, to Excel Reader, to whatever outbound reporting system. And this also is a historian. So it's got a built-in historian, an HMI, it's a SCADA-based platform. So it's recognizable by my user base. And you can name your groups. It's very customizable is my point. So Dean, if you could kind of close that for a moment and go, if you will, to notification on the top, on the left, yes. So I'm the controls manager and supervisor. I don't want to get alarms coming to me for everything. I want to maybe categorize my alarms based upon severity, based upon type, based upon maybe the lines in my plant or the locations in my plant. So I can customize this tool any way I want. I can then allocate who on my shift is to receive what alarm and when and how. So, for example, I have 3 shifts in this, and based upon, again, those parameters that I configure myself, my roster of employees are going to receive either alerts that are yellow, alarms are red. Certainly, I don't want an alarm flooding situation. If I'm the controls manager, I don't want to see it all, but I do want to see when things start to go really, really bad. And again, going back to the Slippy map, the geographic map I showed you, we can support an unlimited number of data sets and an unlimited number of user on this platform. So it's very evolvable and scalable to the point where if the CEO of the company wanted to, I doubt it, but if they wanted to, we could configure a screen for him or her. The C-level, C-suite executive, same thing, to see that particular realm, right? So we can get very granular to the operator level, all the way up to the C-suite, should we choose. Dean, if you could go to the bottom left of the first page. So we're showing you, we're pulling in data. We're pulling every 137 milliseconds, and we're setting thresholds and key parameters based upon the production facility and the process run within the facility. Down here on the left, on the little square. Yeah. No, on the next square, over. Okay, so we can configure this dashboard anyway. If you go to alarms, reports, diagnostics. So I can also, if I'm the controls manager, this is another little feature that we've been working on with our customer in this particular case. Historical notes we can require to close out alarms. Encrypted historical notes need to be inserted into the system to close out alarms. So I can pull up reports showing open alarms, acknowledged alarms, unacknowledged alarms. And as the manager, I can require my operators must place operator notes in the system to show me, so that there's that lessons learned and there's that passing on of information that's encrypted. So this is a very flexible, evolvable platform. From a pricing standpoint, again, forget about that it's Denison doing this. From an architectural standpoint, you're moving from application software sitting on servers that requires typically DBase, SQL running on another server. So more boxes, more software, more operations cost. Now, when you move into a cloud-based environment, even if the cloud is on your location cloud, right? Behind the DMZ, you don't need the hardware. You're programming into this. Your SQL license is going to be substantially lower, and you can make very quickly service changes in a software and a service cloud environment versus application software. And the pricing is always different too. You can pay on a tag basis. So whatever IO tags you're measuring and monitoring that are relevant to you or important to you, versus for software release 1.2, 50 user license, and you might not have 50 people using it. You might have 26, and you might not necessarily need that full feature set. So from an economic standpoint, software as a service is economically substantially different and better than kind of the traditional RTU software-based architecture. So again, this is just another map. If you go to MCC, Dean, this is our one-line power diagram dashboard. If you go to the Slippy map, again, the first page, and pull up maybe another location. I think that's how we built this prototype. Yeah, pull up just the first location. Yeah. Yeah, that's a good one. So we can demonstrate the data in different formats, working with the users on that. So whatever they would like to see, this is basically the same representation in a different way than the one-line diagram. But again, our focal point where a lot of the projects have not really taken hold in power quality are the snags along the way. The snags along the way of not being able to connect to the smokestacks of data. So having a platform that's flexible with hundreds of connectors matters. And another snag might be, well, our users don't like the screen. It's not anything they recognize. That's more human factor engineering than anything. Well, how can we make them more comfortable using that screen so that the insights are acted on and it's not just a science experiment. So this is just another sample. But you can envision technically, if we can program data sets and we can set thresholds, min-max thresholds, if we understand your process, then what we can do then is measure and manage other data sets that are impacting your machines. So recently we had a call with a big pharmaceutical company, and I looked in their annual report and it said, okay, their job is to make lives healthy and happy, kind of thing, through the ages and stages of their life. That was their comment. And I said, well, that's kind of what we do, right? If you think about power being critical to the machine health and your operations health, if we're not measuring and monitoring power, your machines are not going to live as long. Bessie's going to die. So you might have a drive with a useful life of 20 years, but if those sags are hitting him or her, repeatedly, her useful life might be 4 years and not 20 years. So this is a comprehensive way of addressing it. And we took the problem, I won't say problem, we took the challenge of looking at all of the pieces that were necessary to truly solve the problem, from assessment to the monitors to the platform to the next step. And we can exit out of this. The next step is we host this in the cloud. So in a fully redundant, SOC compliant, a secure data center. Yes.
With this cloud-based architecture, do you have a consequential single point of failure?
Well, a point of failure might be in the connection piece, right? Another point of failure might be in your data center. So we have a fully redundant data center that's hosting the data. So that's not a single point of failure. You've got redundancy. Your transmission link is DNP3. So security is always an issue, right? I'm getting to your failure point. And then if you want to design redundancy, you can do that. You can have multiple servers. You can have mirrored servers in any point in your architecture. So nothing is a one size fits all ever. It requires the engineering piece. The questions that people ask are to your question, right? So one of the points of failure would be in how the data is stored, and that would be in your data center. So no, to your question, no, not there. On the plant floor, they're running their operations. We could design it where you have mirrored servers on the plant floor. That could create redundancy, to your point. So no, I don't believe so. It's all in how you architect it.
Well, what's occurring to me is that the monitoring is, trying to think of the right words, might be out of the friendly confines of the plant, so it's someplace else. So between the plant and where was
Your transmission link. Your transmission link.
The link.
Right.
Or what's at the other end of the link.
Mm-hmm.
These are all things that have to be accounted for. So you take that into account.
Mm-hmm. So it's all going to be based upon the nature of the client and what they're doing and the value of their information. And there's always a cost benefit to everything. Or, a big elephant in the room is always going to be security, especially with data. Data's, in my opinion, the keys to the castle. And so we want to make sure that it's redundant and stored, to your point, so that if something were to happen, so that DMP3 protocol I talked about before, not only is it a secure transport, layer 2 transport protocol, but it also affords for time stamping of the data. And so we can timestamp the data, we can store what's relevant versus all the data. All data is not relevant, maybe some subset of the data, and that would help reduce storage cost because, as much as RAM is cheap, it's not free, right? And you're talking big data, so you don't want to store everything. You want to store just something. But to your point, you can architect any network you want with redundancy. It's just a matter of where the data is coming from, where you want that redundancy held, and how you architect that. Geographically redundant, mirrored, there's lots of ways you can do that. I don't know if that answers your question. Every customer is going to be different. And then what's driving when you build communications networks is how much are you spending? Is the cost benefit going to be worth that? So the last slide, is just kind of a philosophical piece. In 2014, John Chambers, the retired CEO of Cisco, addressed the World Economic Forum executives and said, if you all are not thinking of yourselves as data companies, your competitors will. And if you don't start utilizing data more efficiently and effectively, your businesses will be substantially changed in the next 5 years. Now, we know that's the case. Jeff Bezos at Amazon, not a bookseller, a data company, that, by the way, is a grocer, and by the way, is a retailer, and by the way, but at the core is data. They're utilizing data to their great advantage. And in our particular case, we believe power quality plus data is the home run here, because if you're not addressing power quality as a core raw material, energy as a core cost driver, number one, and number two, the integrity of your power, because it impacts the longevity of your machines and your ongoing operations, you're making a mistake. And what we found through working in some of these solutions is that the solution is always multifaceted. It's a Lego blocks you have to put together to solve the problem. To your question before, it's like building a network. You want to build a network of a solution. So there's a three-legged stool when you talk about cloud-based services. You can deliver solutions faster. Your ROI is quicker. Your CapEx and your OpEx is much lower. And that can allow operators to focus on what they do best, operating their business or building their widget, and outsourcing some of these skills to other people that might be overlay to their already limited operations team. And it allows us to move faster. Now, what's on the horizon, which is always the fun part? If we can overlay perhaps diagnostic and health related data on the health and diagnostics of machines that are impacted by poor power quality, then we can correlate that data. We can then start to make really interesting decisions on, well, if we don't improve the power quality that's impacting Drive Bessie, Drive Bessie's going to die. And you can very quickly do the math on that useful life, and then also perhaps even in the very near future, overlay predictive and preventive machine learning algorithms. So you can take that mean time between failure numbers that we know about those machines, and we can then very quickly determine what do we need to do so that our overall equipment efficiency is at or near its peak utilization, right? So we all talk about Pareto. Everybody knows Pareto, right? The 80-20 rule. The best in class are going to be looking at, you know, that top 20%. How do you squeeze the lemonade out of that last 20%, not necessarily the 80% in the Pareto curve. And it's OXE, I like to call it, not OEE, right? Equipment, efficiency. It's how can we utilize our resources more efficiently, whether it's people or machines or water or energy. In this case, energy is the big common denominator here. So I'm going to stop talking. But we believe if you focus on the value drivers, the solution sets become obvious, more obvious. And power quality is that important. So thank you for your time. And any Q&A, I hope, Matt, you're still there, please. He's
Yeah, I'm
fired
still
us.
No, I'm still here.
Like any questions, anybody? Eric?
Yes.
You talked a lot about the need for upsets being a main driver for the need for power quality or power management, power quality management. Are there tools available to the people locally to troubleshoot problems, or is the idea that the data is stored and a third party is able to go in and review the data to determine what the root causes of the upsets might have been? You've got motor starting, knowing it's nice to know what your voltage is and your harmonic distortion, but a large load, you're going to need more data than just the power readings. You need to know events. Is that something that's available to the operators locally, or is that something that you have to go and mine later?
Okay.
With other software to determine what the root causes of those upsets were?
Okay. Good question, because I know we all are coming at this challenge from slightly different perspectives. Think of us as we like to play with Legos. My daughter asked me the other day, what the heck do you do? Well, we like to play with Legos. So if you're playing with Legos, you want to create your box so that it's scalable and evolvable, and you can parse the Legos, for lack of a better word. So what we've done here with our solution is we've said, look, we just want to make people aware of power quality issues and kind of going through this TQM-esque type solution map. To your question, though, can you have the data resident, or does it sit in this big hand-waving cloud place? It can be in both. We can go in and use our software, use our application, work with a client. The data sits behind their DMZ, so the operator can start to look at what's going on, and we can work with, Matt can work with the operator on the function and the process to understand what's driving it. If there's another issue, we can program that into our platform, and you can store the data resident should you choose. Does that answer the question?
Can I jump on that too, Diane?
Yes.
Yeah, Diane is absolutely correct. I have worked with clients who don't want a part of what's going on. We house everything and we examine it and so on and so forth. They only want to know if there's a problem. Then there are those clients who want to know what's going on every step of the way. And either way is fine with us. It really is, what does the end user want to do with this? And like Diane said, you know what, if it comes to a point where like, listen, we can't figure this out, or we don't have time to figure it out, then we're happy to jump in and help whatever you need us to do. But to Diane's point, it's completely scalable. We can fit the process, the cloud-based system to whatever you want. You can do with it what you want. If you want it to be intuitive for you, then it can be intuitive for you. Absolutely.
Or you can outsource, like you would an AT&T, for example, and pay for a service and have, a monthly service with a mat that says, okay, this is what we're getting. We're seeing your alarms. This is what we think. Remedial actions to fix the problem. It could be scalable, and the data can be housed with you all and run with it. We can license that, or hire us to help you, or some combination.
But if I'm getting SAGs all of a sudden, and I need to figure out why, is that sort of is that solved by examining the data, or is it something that's easily managed at the local level? Even if I have to go to the cloud data, can I troubleshoot those sort of issues? Or is that you still, do they depend on engineering support to troubleshoot?
Yes.
Okay.
Yes. So for example, we had a pretty hard problem to address with some failures, and part of this challenge is finding out what the root cause is not, right? So we know we're not chasing that squirrel. And then narrowing down what the root cause of the failures could possibly be. And that required a lot of work with the OEM, with Matt, with different, with the operator, with the customer, saying, okay, this is what we think. Is this happening? So the data is important, but it's not the cheese stands alone. The knowledge of the engineer needs to be there too in the process, if that answers your question.
But in the case of a system, I mean, a lot of times you do have an operator interface there on the plant floor, in addition to what you have in the cloud. And then also
right.
on the plant floor, you have alarming capability and alerts. So
Yeah.
you have sags and swells or something you were trying to look at. You can
Right.
set alarming thresholds for sags and swells, and
What you could also
let someone
do
know right away.
to that point, the cut and pasting piece of this, the Lego piece of it. And I don't know the situation, but let's say, to Dean's point, you have an HMI screen on the plant floor, alerting, alarming, thresholding, all of that. So your operators see that. You can have the alarming and the alerting also going to us, where we're looking at all of that, and that information can go to a Matt. So Matt could be assisting that same client, saying, okay, this is what we're seeing in terms of diagnostics, right? Or someone in that group. This is what we believe might be happening. How do we troubleshoot this? So you could do it in different ways. And often what we're seeing is resources on the plant floor are typically focused on maintenance, mostly day-to-day, just making sure things aren't breaking. Many clients, they're not all oil and gas. They're in different vertical markets. They might have limited knowledge base. Their breadth might be not necessarily as tenured, right, as some of these people. So having that overlay service would be helpful to them, useful to them. I know that's not one size fits all, but we're not a one size. I wish we were.
All right. Any other questions? All right. Well, thank you very
Perfect.
much for
Thank
coming
you.
out. Appreciate it.
Thank you. Thank you.
For everybody that joined
Thank you.
online, and then you'll see our next meeting is again in October the 10th on a Wednesday, and we'll have John Lawrence Bush in talk. So thanks for everybody for joining.